Welcome everyone. Just letting everyone of our guests into the meeting room. Thank you for joining us on this Monday for our second session, which is the later session and designed for our partners up in Southeast Asia. So thank you to all of those who have joined us. Today we're talking about fast set concrete products. Just waiting for a few more people to pop into the meeting room there. So it's based on calcium sulfo-aluminate technology, which provides its type of cement that provides rapid cure, long-term stability, a low carbon footprint, less energy to produce than OPC cements. It's chemically resistant, and it also has worldwide usage over a number of decades now throughout USA, Europe, and Asia. FSC, fast set concrete, what is it? What are we talking about? So it uses that CSA technology. It's a fast set cement binder system, and we use that binder to form a range of products. Products ranging from fluid grouts, which have really pourable, highly pumpable consistency, available, in 20 kilo packaging just to mix water with. Micro concretes as well, with small aggregates that can be used for small repairs, also a pre-bag product. Structural concrete, which is applied using weigh batching units, which we'll go through in this presentation. And we can also produce sub-base or lean mix for road applications. So there's a range of products that can come out of this fast set technology powder. It's just a new type of cement system. So looking at the Australian experience and what we've completed here, and this is for our Southeast Asian participants, just to give you a bit of an update on what we've done. So back in 2005, it was probably one of the largest single applications of a fast set grout in the country. And that was when we upgraded Sydney Airport in readiness for the A380s, which were coming. And you can see there a picture of General Holmes Drive, which is a tunnel which runs across the main runways and taxiways. Quite a length to it and crosses quite a few taxiways. Had to all be upgraded over a 6-month period for strengthening, and a fluid grout was used in that application to cast in precast beams, which would strengthen the actual tunnel. So that was the first really large application. And in 2012, there were airport slab replacements which were undertaken, and that was the first use of a volumetric truck. And the volumetric trucks were a little bit in their infancy in Australia and have come a long way in the last few years, through to 2017, where we've had the first mobile weigh batching units. So they actually weigh the products as they come out rather than relying on volumetric scales to measure. So a lot more accurate by the time we got to 2017. And then on the back of this accuracy in 2018, we saw a lot more application in airports, but also approvals by road authorities in Australia to use this for road slab replacements, these products, knowing that they could get the reliability. So why do we need fast set concrete? Fast setting cement products, through acceleration already exist. They're accelerated using calcium chloride and other types of accelerants. We want to avoid those because from a durability point of view, it's not the best way to place concrete when you're looking at long-term 20, 30, 100-year design life. We want to eliminate traffic management diversions. So as you can see in the photo, the quicker we can return a slab to service, the quicker we can get traffic underway. And we want to do that upgrading without lane and runway closures, particularly in airports. You only have a very small window of time where you can do the slab replacements, and that means that the concrete has to achieve its strength within a few hours to be able to land a plane on it. And the types of places that we use it, a few photos down the side showing different applications, but it boils down to road repairs, widenings, new construction in roads, railway shutdowns, emergency repairs, airports, as we spoke about, bridges, stitch pours, maintenance, bearings, and other things that need to be completed with a fast turnaround time. Tunnel progress activities. So where in a tunnel, you need to have fast turnaround times to progress the tunnel, a fast set concrete system might be the solution. And really any work that requires a speedy return to service involving a cementitious product. So some of the advancements that have been made over the last couple of decades in this area is that the manufacturing process has improved a lot, so we can get far more repeatable results out on site in terms of strength gain and durability as well. We can demonstrate a 100-year design life for these types of products. We've shortened the mixing time, which makes these products suitable now for volumetric mixer application. I'll talk about that as well. And we can achieve consistency in all conditions. So the set times, the workability, and the strength development, whether we've got cold temperatures in the south of Australia, down in Melbourne or Tasmania, or whether we're working in Singapore or the Northwest Shelf at 30, 40 degrees temperatures, we can still achieve the same sort of strength development and set times. And we'll talk about how we achieve that as well. So let's have a quick look at the manufacturing facilities. So the powder blenders that we use for this cement technology has to be capable of mixing multiple small ingredients very thoroughly. So the types of cement blenders we use are actually from the pharmaceutical industry, not from the cement industry, because they're more accustomed and better designed for mixing the product thoroughly. So the type of mixing devices are really important. On top of that, we have a lot of controls in place over our raw materials that come into the factory upon delivery, but also we do a range of testing, not only during manufacture, that's an obvious one. Every time you manufacture the product, you have to do your full range of testing on each batch. But in addition to that, we're going through the factory. Every month, we're pulling out all the raw ingredients and we're doing type testing. Now, type testing is something you would normally do once when you develop a product, but we're now doing this every month. And the reason for that is so that we can have constant data on the raw materials we're using in advance of them being applied on site. So we will already have the 28-day strengths before that product is manufactured and sent to site, which means that we get much more reliability and can identify trends and patterns in the raw materials over time. So we've got that data, which is being done monthly, and we're also testing every single batch that comes out. And when we say every single batch, each batch would be around 1/2 a ton of powder. So that's a lot of testing. And the type of testing we're doing, just to summarize some of those tests here, we've got powder consistency, we've got dimensional stability testing during the plastic stage, we've got shrinkage testing, bleed and segregation, hardness, and then obviously the mechanical properties of flexural strength and compressive strength. And doing that testing early gives us the opportunity to get that long-term testing before the product goes out to site and is put into application. Durability for a longer design life. Now, I've got to say that 20 or 30 years ago, it was hard to believe that you could achieve fast set and a highly durable product all in one. It seemed as though you either had one or the other. But now we can actually say that we've got fast set products that are durable, will last the life of the structure. Previously, there were issues associated with fast set. People would see that you would get cracking, thermal and plastic, you'd get surface dusting, loss of strength over time, and they wouldn't provide any protection to the reinforcement because either they had, chloride-based accelerators which would attack the reinforcement, or they wouldn't be alkaline, so they wouldn't provide that alkaline environment to passivate the steel. So these were all issues that were associated previously, going back maybe even 10 or 20 years. Now you don't see that. CSA cements are very, very low shrinkage after initial set. We're talking shrinkages of around 200 to 300 microstrain, much, much lower than what you see out of concrete. But the standard shrinkage test in that regard isn't fully adequate. It gives you an idea of the shrinkage that happens from 7 to 28 days. And yes, CSA is a very low shrinkage in that zone. But what's happening in the first 7 days, and particularly with something that's curing so rapidly, you really need to know what's happening. So we do a volumetric stability test during the plastic stage, and we're actually monitoring the volume movement and change during those early stages, because we know that that's a high risk with calcium sulfur-aluminate cement systems, is that you can get plastic cracking in those early stages. Some of you may have had experience in seeing that out on sites. If the product is developed well, you won't see that plastic shrinkage cracking. So all of this leads to us looking at how we can determine the 100-year design life. And there's a lot of factors that we've tested and put forward as reasons for making that assertion. So the shrinkage on the product, as I mentioned, is less than 300 microstrain. We have a very low chloride content, so we know that's good for the steel reinforcement, less than 0.005%. It's low in soluble alkalis, and we have no residual sulfates. So the lifetime outcome for those items is that you have no surface cracking, you have no alkali silica reaction, concrete cancer, and you have a high resistance to sulfate attack. So we know that those bases are covered. We also complete NORD testing, and we know that we have a very slow migration of chlorides through this type of cement system. We know that it's very high density, and we know it's low in permeability. So we also have no surface dusting and excellent wear resistance. So again, all lifetime properties that we know will lead to a longer life outcome. On top of that, we've done long-term testing on pH. So we know that the alkalinity is maintained for more than 900 days. And we also know that we have a 900-day strength increase, and both of those things lead to protection of the reinforcement and a durable hard-wearing surface. On top of that, and finally, we know that we have no late formation ettrinite, which can be a question around CSAs and needs to be tested for prior to delivery of the product. So what we look at is the long-term testing, and most people are only interested in cement, fast set cement. You know, what's happening in the first few hours? What's my strength at 2 hours? What's my strength at 3 hours? Sometimes they might ask you, what's my strength at 28 days, but not very often, because by then the product, the item is usually put back into service and forgotten about. But long-term strength gain is actually really important in these products because the reaction actually continues over a reasonable period. In fact, the strength keeps gaining for many days. You know, we've gone past our 28, 56, 112, 224, 448 days, and we're still seeing a strength gain. So there's still something happening within the product. There's still a reaction occurring. And we know that doesn't level out until around 500 days when the reaction is complete. So what we want to make sure of is that the actual reaction that's occurring between 28 days and 500 days isn't having a negative impact, because we know that that's when ettrinite is forming. And if you have an oversupply for that ettrinite crystallization, then it can break down your cement structure. And if that breaks down your cement structure, then it can lead to a reduction in strength over time, like this. And this has been seen, if we go back maybe a decade, 2 decades ago, in some CSA systems where the strength gain after a couple of years was noticed to drop off and there was powdering of the surface and a reduction. So this is something we avoid by doing the long-term testing. As you can see, just tabulated the strengths. The testing was completed both at 0.2 and 0.25, so we went the high end and low end water ratios, and you can see that we've got strength gain all the way through to the 900 days. That testing is still ongoing. We know there are no changes now, but we still would like to keep testing that, and we're about 5 years into that process. So looking at some of the application systems, I mentioned volumetric trucks earlier, and these have changed the way we apply fast set products, but in themselves, they've also changed, particularly over the last 5 years or so. So what it is you have powder and aggregate bins, which are separate. So you have your powder, your cement powder, and your sand and aggregates, which are put into separate bins. They drop down into an auger, and then that's mixed off a conveyor belt through that auger, and the mixing actually occurs at the point of placement. So we're not adding water to our powder until we're actually ready to place the concrete. And what that means is you have unlimited travel time with the products. Whereas if you were using a concrete agitator truck, you would have to put all your powders in, put your water in, and drive it out to site and hope you got there fast enough before the product went off in the truck. So that's the difference with a volumetric based truck, which has now turned into a weigh batching unit, because there's been some equipment advances in this area. We now have computerized mix design and calibration, so it's all controlled by a computer. The trucks can move and pour continuously, so you don't have to stop the pour to move the truck forward. And that's a really important feature to maintain consistency of your pour and avoid cold joints. And we also have continuous weigh batching on the powder bins, which is what I mentioned was the really big advancement where we went from volumetric trucks to weigh batching units. And what that means is that on your powder bins, you have load cells, which are continuously weigh batching the powder as it's delivered from the powder bin. And it gives you really high accuracy on that powder delivery, which combined with electronic controls over your water delivery gives you an extremely accurate water cement ratio all the way through your pour. So you know you're going to get the strengths you want, you know you're going to get the consistency you want all the way through the delivery of that product. Besides the trucks being advanced, we've also had material advancements, as I've touched on already. So the total mixing time now is less than 20 seconds with these trucks, as opposed to with an agitator with truck, which might have been mixing for even up to 20 or 30 minutes before the concrete was poured. or where you're using a grout mixer where you had 3, 4, 5 minutes of mixing time before you had to apply it. Now you can see in that photo the little black section there, which I'll point to with my arrow, this section here. This is an auger in here, and the powder and the water all gets delivered into that bottom point there, and then it gets shuffled up this chute, and as it's getting shuffled up by the auger, it's also mixing at the same time. But it only allows around 20 seconds of mixing time. So we've had to put additives in the product and change the way it was designed so that we can improve the, let's call it mixability of the product. So we've changed the ingredients to suit that application. And full mixing means that you achieve more consistent results. So you're getting more consistent set times, you're getting more consistent rheology, and you're getting more consistent strength gain. And mixing is a really important part of that. We've also added some changes to the raw ingredients. One thing we realized was that the product itself on mixing was changing in its rheology over time. So as it came out, it had a fairly low slump. And then after about 2 or 3 minutes of vibration, it had a really high slump. And what we're finding is that the plasticizers that were being added in a powder format were taking a few minutes to dissolve. So we actually converted those to a liquid plasticizer, which means that they were active immediately. They're part of the computer-controlled delivery process with computer-activated pumps so that we know we're getting the right delivery of plasticizer. And that allowed us to get a much more consistent product for finishability, workability, and spread as well in the slab. So we're getting much more consistent results in our rheology now. One of the biggest changes we've made though to the product is the liquid dosed retarder. So the product has always been retarded using a powder retarding agent, which was added at the factory. Problem with that is once it's added at the factory, it didn't matter whether you had a 40-degree day or a 5-degree day, which honestly can happen in Melbourne, just wait for it to change. You were stuck with that powder that was delivered. You had no control over it. So every 10 degree of temperature change in the ambient temperature would either double or halve your set times. So if you were hoping for a 30-minute set time and suddenly you had temperatures which were 10 degrees hotter than what you were expecting, you would only have 15 minutes of work time. And that's a pretty big hit to take in terms of the amount of work time. And then on the other hand, it could go the other way as well, where you don't develop the strength in time. By adding a liquid retarder with controlled dosage through the truck, we can actually set the amount of retarder that we're adding to the powder so that we can set the work time to suit the ambient conditions. So whether we now have a 5-degree day or even closer to 0-degree day, we can make pause, or a 40 or even 45-degree day, which we've worked in before, we can actually have a set time set at 30 minutes or 40 minutes as per the contractor's instructions. So we can now modify the set time on the product to suit the ambient conditions, which has made a really big change to the way we use fast set products. Just a summary of the properties that we achieve in terms of compressive strength and flexural strength at the different times, just in this table here. Again, this presentation will be available for download. There's a link on our website, and Aidan will pop that link up now just in the chat, as you can see there. So you can click on that and just request a copy of this presentation and other information as well. So moving on to site testing, just to finish up, and I won't go into too much detail on this because we're actually presenting in full on this topic tomorrow at the same time on maturity testing and why it's required. But site testing does come with some challenges when you're talking about fast set products. One, the work is being done of an evening, so your laboratories aren't naturally open. They have to be open for the work. On top of that, you can have cold temperatures. You can also, it also means that you have to transport the cylinders quickly to the lab without damaging the cylinders or having an effect on them. And the chance of that cylinder being representative of what's happening in the slab is pretty limited in this type of application when you've got such fast set gain. And what we'll show tomorrow when we're talking about maturity testing is that there's a difference in what you find in cylinders compared to what you're seeing in the slab in terms of strength development. And there are ways around measuring that. So we need real-time data when crushing these samples is what it boils down to. The cylinders have low exotherm They actually hold a lot of the cool. They don't allow the concrete to generate its natural heat, which means there's a lag in cylinder strength over the first few hours. So the cylinders aren't truly representative of what's happening in the slab. Cylinders are old technology, and that's why we needed this newer system for 2 to 3 hour measurement, which is our maturity testing. And again, we'll talk about this in the maturity testing presentation. It was developed in the 1950s, so it's got a long track record, but it's really only been commercialized more recently, particularly with the advent of wireless and Bluetooth technologies, which has allowed us to put probes into our slabs at a fairly low cost, and that technology can then provide real-time data in terms of the strength gain so that we can have reliable information on when to know to open our slabs to traffic. So really interesting topic this, and some great advances in the technology, which we will go through in the maturity testing presentation. So just in summary and finishing up, high early strengths and durability are possible, all in the one product. We can achieve greater productivity, even though we have limited access by using fast set concrete and cement products. We have a lower lifetime cost than using a calcium chloride accelerated product, and we can now achieve very consistent quality and delivery, and particularly with the backup of that on-site testing, which can be accurate and in real time. So a lot more reliability around fast set products, whether you're having them delivered by a weigh batching unit for a larger application, or even if you're just mixing a 20 kilo bag of a grout or a micro concrete, you've got a lot more reliability in those products. Okay, well, it doesn't look like I have any questions. We've got the link there that Aidan has posted. Feel free to click on that and request some more information. We'll have a copy of this presentation available, and also the video of this presentation will be uploaded for download on our website, on the website webinar page. Thank you very much for joining us. It's been our pleasure to have you. Thank you.